Okay, so let's get started. Um, Thank you all for coming in this unusual late for our seminars. Today, actually, it's a strange occasion because we have someone who has to from Zurich all the way here to London to present his work. Leonard Bauersfeld, he's from University of Zurich, and he has done some impressive work with drone racing. And he's gonna be telling us how they achieve it in their team. Today, I want to make a special thanks to our sponsors, Iban and especially InstaDeep, because it is thanks to them that we could bring Leonard today. And remember, also thanks to them, we have some food at the end of the talk. And without any further ado, I let Leonard start. Thank you very much for coming.
Thank you very much for the warm welcome to London, and good afternoon, everyone, and welcome to the talk on champion-level drone racing using reinforcement learning. As you can see by the list, and as you can probably guess, this work is not just one man's work, but as nowadays common in research, there's a lot of team of people that have to work together in order to make this possible. So the work that I will present is essentially a collaboration with my PhD colleagues Elia Kaufmann and Antonio, as well as then my supervisor David Escaramuzza and Matthias, as well as Ladlen from Intel. So a lot of people involved here that made this possible, and yeah, thanks a lot to the great collaboration. Drone racing itself is an exciting sport. It is exciting not as a PhD to work on, but it's also exciting as a sport to be part of and to play in the real world. So what is this drone racing? The idea of drone racing is that you have two drones that race at the same time, head-to-head against each other, and they need to pass a sequence of gates that you can see up here in the correct order. If you've done so, you win the race if you are the first to win the race, which means you are the first to complete a number of given laps, and then you have beaten your opponent in drone racing. Now, the question here is, how good are humans actually at that game? And then also, why is it even interesting to work as a roboticist or as an AI problem? And if we look at how good humans are at that game, I can tell you one thing, they're remarkably good at that game. What you can see is a human expert pilot racing through the BMW world in Munich without crashing into the valuable cars at speeds of about 100 kilometers per hour on the long straights. All that these pilots have to orient is these gates, which they know they have to pass in some order, and they have to be able to do these crazy maneuvers in order to fly there as fast as possible. So while this is certainly an impressive feat to achieve for humans, and one I could never do myself, the question is, why do we want to work on this as a roboticist? What is the point here? Why is it important for drones to be able to do something like this? And the main idea here is that drones need to fly fast in order to get something done. In contrast to cars, which have very low fuel efficiency if they go very quickly, drones are quite the opposite. Drones, in fact, have the most efficiency if they fly at reasonably high speeds. So if you fly at speeds of around 16 meters per second, which equates to 50 kilometers per hour or about 30 miles, then you get the most range out of the drone, which means you can cover the most distance. And covering a lot of distance is very important for many tasks where drones are a promising device to use. For example, an inspection task along bridges, you want to cover as much bridge as possible per battery. If you have a search and rescue scenario, it's important to get there not only fast, but also to be able to cover a reasonable amount of distance. So as you can see, flying fast is important for drones. Why vision-based then? I mean, okay, flying fast, so agility is important, but why vision-based? At the moment, if you look at what current drones do, about 99% of the drones are either controlled by human expert pilots or by GPS, and both is an issue. We have many tasks where drones can be important, inspection tasks, search and rescue, etc. However, we do not have enough good drone pilots. If every single inspection task in the world needs an expert drone pilot to fly the drone, we run out of drone pilots, and this doesn't scale well at all. What we imagine here from a robotics perspective is a lot of vehicles doing a very important task quickly and efficiently. So we need autonomy. Why not rely on GPS? Well, GPS is nice, but GPS in the end is simply a static map. It gives you coordinates of where you are in space, but it doesn't tell you anything about your actual environment. Oh, there's a new obstacle in your way. Well, GPS doesn't know, neither does Google Maps, right? Vision is the only sense that's always up to date, that allows you to actually perceive your current environment and not a pre-built map or just localized within a pre-built map. And at the same time, especially if you fly in indoor scenarios or if you imagine flying in a disaster zone, having no GPS requirement is a very critical point. So this is why we want to work on agile, vision-based flight. This is kind of the vision that the lab I'm working as has been pursuing for many, many years. The challenges, if you want to be able to do vision-based flight, are very high. First of all, you often have a low light scenario, especially during drone racing. You can see it's fairly dark here. Given the low light condition, you have a lot of motion blur that you experience due to the longer shutter speeds that are required for the camera to take in enough light. You then at the same time encounter high dynamic range scenarios. For example, like this, there's bright lights in the scene as well as very dark parts. So you have a very large dynamic range that the sensor needs to capture, and you have low texture environments. All of these make the perception challenges quite big. You also have challenges from the control side here. If you look at drones, they're inherently unstable. Airplanes, for example, they fly without control input reasonably straight. They will diverge after long periods of time. Drones are quite the opposite. You have to control drones at update frequencies of roughly 100 Hertz, otherwise the system will become unstable and simply diverge. And in these scenarios, data-driven approaches, as you can imagine, have shown to excel, especially for the vision part, but also for the controls part as well, because they are computationally lightweight compared to big optimization problem solutions. So what you will see in the following presentation is mainly how deep learning has enabled us with reinforcement learning and classical supervised learning to beat the world champions in human drone racing. To get there was a long way. I'll just show a video from years ago, before I joined the lab actually. So this was the fastest that a drone has ever flown in that year. This was kind of the world speed record for autonomous drones. And you can see it's actually not that fast, because back then it was still an exercise for the PhD students to run after the drone and catch it in case it goes wrong. So we've come a long way from this, or we had to come a long way from this speed in order to be actually able to compete with the human champions. What you will see now is an actual drone race. And in red, the human, in blue, the AI. When I play the video, you have to watch quickly because it will not last very long, basically, what you can see. First of all, we play this thing in real time and you will immediately see whoosh and then, well, we have taken off. Now let's slow this down a bit. And you can see the AI drone, of course, launches a bit quicker because it can go immediately full throttle and doesn't first have to gently move up the throttle like a human pilot. But what happens now is crazy to me. How can humans be so damn good at this? Why is it possible that someone controls such a tiny vehicle at those high speeds? And I mean, not the AI. The AI is impressive in itself, but we have to appreciate the fact that humans are even able to pull this off. What you see here is the onboard video from the drone, from the human occasionally, easily recognizable by having the other drone ahead. So the human is mostly behind during these races. But nevertheless, the human is able to really give the AI drone a good race. And what you've just seen was the world champion in drone racing, racing against our drone. So how is that possible? What system enables an AI to compete at this ridiculously high speed against probably the world's best pilot? If we look at the drone itself, it is identical to the human piloted drone. So both drones that we use have a weight of 870 grams, thrust of about 40 newtons, which gives them a thrust to weight ratio of 4.5. For comparison, Formula 1 cars cannot accelerate with more than 1 G. This thing accelerates at 4.5 G. And even the most extreme roller coasters only go up to like 4.7, 4.8. So this thing is kind of crazy. At the same time, everything that you have seen has been achieved only with this onboard compute and onboard sensing. There's no external state estimation going on. There's nothing on the outside world that this drone needs to fly. It needs a racetrack and everything else is on board. So we have an NVIDIA Jetson TX2 for processing, and then we have a RealSense 2T65 for computer vision as well as state estimation. The 2T65 is quite a nice camera. It has a field of view of 170 degrees diagonally, so it nearly sees the entire half plane in front of it. At the same time, it's a global shutter camera, so that's also really convenient, especially at these high speeds. And finally, with the 2T65, you also get a VAO pipeline supplied by Intel directly, which you can use kind of as an, let's say, initial estimate together with the IMU measurements. How can we use this drone to fly fast? If I would have given this talk 5 years ago, then probably the pipeline would have looked something like this. This is the classic see, think, act cycle, as it's called in robotics very often, where you have three distinct sequential phases. You have a localization phase where the robot tries to localize itself with respect to the environment, understand where it is in space. Subsequently, you have a planning phase where you use the information that you just obtained where you are in order to plan a path towards your goal. This, in this case, would be towards the next gate to complete the lab as fast as possible. And then the last part that you have is the controls part, where your job is essentially to understand how can I execute a command to my, or how can I send a command to my robot in a way that it executes the planned trajectory. This would have been the classic approach, and it is very nice because it has very high explainability. You can understand each of the modules separately, you know what's going on here, you can check the localization, how accurate it is, etc. However, the big downside here is you have very limited robustness as errors are able to propagate. Imagine the localization pipeline being off slightly. It outputs the wrong position, but the subsequent planning and controls pipeline can never fix the error because they don't know about the error. So the modules are too distinct in order to be able to have maximum robustness to harsh initial conditions, harsh environmental conditions, etc. So more recent, especially if you want to get the papers published in machine learning conferences, you would go for something like this, end-to-end control. It's a very shiny thing, and there's applications where end-to-end control is really able to excel. However, there's a small problem here. You could, of course, directly try to map the images or the IMU information as well to control commands, but the explainability is really, really limited, which makes the system not only hard to develop, but also hard to optimize towards the ideal lab time. Because if you want to do something like this, you of course have to be able to fine-tune your system and adjust quickly to challenging real-world scenarios. The last problem is it's very compute intensive to train something like this, because if you want to go for a learned controls policy, and instead of a classic controls policy based on optimization routines, then you would have to render all of these images continuously while you want to train your controller. So that's extremely compute intensive and is prohibitively expensive, so to say. Instead, we went for something a bit in the middle. We have a classic localization pipeline, which is supposed to give a state estimate, as well as then a joint learning-based controller, which takes the current state estimate and directly produces control commands without having to go through the intermediate representation of a trajectory or some kind of planning in three-dimensional space. As you will see, this has very nice properties in terms of how you can train the policy, because this one is a state-based policy now, as well as very good properties in terms of robustness that can be trained into it. So the localization system itself is, well, as I said, pretty much a classical localization system. We have the IMU information available from the real sense camera at 200 Hertz, as well as a VIO, so visual inertial odometry, where the camera itself as a black box fuses the IMU information with some kind of feature tracking that it does on board chip. The system here gives you an output of the position and the state of the drone with a rate of 100 Hertz, which is pretty good. The only problem is it's not that accurate because at these high speeds, it essentially is only forward IMU integration, and it does not seem to have very good feature tracking abilities. Note it's a black box from Intel, so we don't know the exact details. But you can see here the green trajectory is the estimate from the VIO pipeline of the real sense versus the blue ground truth trajectory. You can see that there's quite a bit of drift, and already after one lap, we would not be able to fly through any gates. So of course, we need to address that. In order to address that, we can use a gate detection network, because the thing is, you know where the gates are. During a drone race, the racetrack doesn't change. So it's a fixed racetrack with previously known gate positions. So if you're able to detect these gates, and we've done that with the CNN unit architecture, you can then use these gate positions in order, well, you can see how we can detect them. You can then use these gate positions in order to triangulate yourself with respect to these gates. So you know where the drone is, and you can then use something like a PNP, so perspective from endpoints. There's a special solution for 4 planar points called IPPE. And if you use this, you can triangulate the pose, the orientation of the drone with respect to the gates in front of it. So that's a very nice feature that we have there. Now we do what every engineer does. If you have 2 sources of information, one coming from the gate detection, one coming from the VIO state, we put a Kalman filter there. The Kalman filter itself needs covariance estimates, which we can get from the gate detections by essentially Monte Carlo sampling a bit the gate positions. or the corner positions that are detected, and thus we get a pretty robust estimate of how accurate our current estimate is with respect to the position. To show how this works, what you can see here is the covariance ellipse of the fused estimate, and you can see the drone flying around as well as the gate detections being shown, now slowed down by a factor of 0.25. You see, once we approach a gate, the ellipse shrinks because the closer you get to a gate, the more accurate you're able to estimate your position. And then after you fly a bit further away from the gates, the ellipsoid again grows and shrinks again when you approach the next gate. So with this system, we are able to quite robustly identify where we are in space. And also we have gotten rid of any scale or any drift, simply because we have absolute pose measurements from the gate detectors. Now, with this, let's come to the next module in the pipeline, the learn control. So the perception system gives a state estimate, and this state estimate is now fed into the controls policy that you can see here. So the controls policy itself is realized by a multi-layer perceptron network, a very small one, only 2 hidden layers, 128 neurons. And the policy network sees the current state of the drone, so position, orientation, velocity, body rates, as well as the previous action that it has given. Inputting the previous action to the policy, so the previous control command, is very important in order to ensure that the policy generates smooth commands and does not give jerky commands, which are very hard to execute for the drone. Then these control commands get sent to the drone, and then the drone state basically gets sent back in the real world to the perception system so it can run the cycle once again. The commands that we use to control the drone are collective thrust and body rates, which means if you have a quadcopter, you say how much thrust in total all 4 motors have to generate, as well as how quickly the orientation has to change. So you supply a pitch rate, a roll rate, and a yaw rate. This is much superior compared to another control modality like angles or even just velocities, because it really maximizes agility. Essentially, the representation of a collective thrust and 3 rates, if you have, that's 4 commands that you send for 4 motors, is a good representation because it means you have maximized the degrees of freedom that your actuators basically supply you. There's a unique mapping from collective thrust and body rates to motor commands if you neglect saturation. In a saturation setting, things become a bit more difficult. Now, how can we train this policy? So to train this policy, what we basically do is we have a simulation environment like most RL people do. And in this simulation environment, we have implemented a physics engine, and we also give the rewards. So during policy training, the policy commands an action. This is fed into the physics engine. So the physics engine computes how the drone would fly. And then subsequently, the rewards basically judge how good this control command was and tell the policy how much reward it gets. All of this is done in a purely state-based way. So there's no need to render any images at this point, because the localization pipeline anyway supplies the state to the policy, which makes the training really, really fast. Some details about the training. It's a reinforcement learning training which relies on very few rewards. It's a dense reward, a dense shape reward. What we use is primarily progress. So we essentially give a reward for decrementing the distance towards the next gate. We also give a reward for looking at the next gate, because if the drone doesn't look where it flies, the VIO system, and especially the gate detection pipeline, has a big problem. So reward is given for looking towards the next gate. Then there is a command reward, which basically says, please give commands very similar to the last command, and do not give crazy commands. So we also penalize the norm of the command. And finally, there's a reward that basically says, don't die. Dying happens in 2 cases. You can either crash into a gate or you crash into the world bounding box, which means ground floor ceiling, as well as the left and right walls of the arena where the races happen. This whole thing is then trained with PPO. So we basically use a bone stock version of PPO, nothing special here. 100 million environment interactions are roughly required, which amounts to 50 minutes of train time on the CPU for the simulation, backpropagation the GPU. So the drone learns pretty quickly. And in total, it accumulates like 23 days of flight time in simulation within this.
That's a question.
Yes.
You say here the volume policy network architecture. Did you try to validate them, or it's just started with this before them?
So yes, the value and the policy network share the same architecture. It doesn't mean that they share the same weights. Yeah. They both get the same inputs. We've tried to give the value network more inputs. However, more inputs don't really help, as the full state of the drone already describes the entire problem. So there is no real benefit to give the value network more information. We've tried experimenting with larger value networks, Nevertheless, in the end, it turns out pretty similar in almost all cases. So
you did an experiment that's the same size but independent weights for the two.
Yes, they have independent weights at all times. We share the architecture, not the weights. It's basically both a 2-layer MLP 128 hidden layer size. So that's the architecture that we went for. If you watch the training progress, what you can see is initially there's complete chaos. The drones have no idea what's going on. But then as the episodes progress, you can see that the drones slowly get used to flying around the racetrack here. You can see that after a while, they really converge towards a single track that they like to follow on. And this is kind of the result that we deploy in the end. The last half of the training is really used for fine-tuning the policy, and it gets really dialed in on how to fly the track perfectly. For those who wonder why is there variance, we of course train with domain randomization. So different episodes see slightly different masses of the drone, slightly different moments of inertia, slightly different thrust levels, etc., in order to make the policy robust to various, say, real drones, or various possibilities of how the real drone might behave. Depending on how often it crashes, it has more hot glue on it than the other drone, for example. So, different masses, etc., are a thing in the real world. Now, if we train with this and we basically deploy the system as I've shown it to you now, we will see in a moment that there are some problems. And these problems arise from various things. So let's have a look at the physics engine behind this in order to really understand what we can simulate and what we cannot simulate. So the physics engine that we use is all written from scratch, and essentially it models the low-level controller, which is on the drone. So this low-level controller takes the control commands, collective thrust and body rates, and converts them into the motor commands. This is essentially a PID controller with a bit of weird aspects to it, because it's really optimized for human pilots, and it turns out humans don't like standard PID architecture like control engineers like. So they've done a lot of weird stuff. For example, it deletes the I part if you reduce the throttle to 0. So there's like a few of these weird optimizations that human pilots seem to really enjoy when flying. Next thing that you need, of course, propulsion system for the drone. The motors are modeled as a first order system, and we also include an empirical power model by measuring about 40 different motor propeller combinations, so we can really predict how much power the system will draw. The benefit of this is, if you combine it with a gray box battery voltage model, also identified on a lot of real world data, that you're able to really model the voltage drop of the battery under full load. And this is an important aspect, as these drones draw over 2 kilowatts of power from one of these tiny batteries. So that's an insane amount of power, and the responsiveness of the motor depends also on the battery voltage. Then we model the propeller thrust based on the motor speed omega here, and we use a fairly simple model here. So this is purely a quadratic model in the sense that the thrust and the drag experienced by the propeller are assumed to be proportional to the square of the rotational speed. I mean, of course, if you know a bit of aerodynamics, you see this is a gross neglection of pretty much everything. There's no such thing as body drag in here. There's no such thing as dynamic lift, which means if you fly forward, the propeller gives you a bit more thrust, actually. There's no rotor-to-rotor interaction. It neglects a lot of things. Now it's possible to do very fancy computational fluid dynamics simulation in order to be able to obtain all of these effects correctly. The problem is, if you want to do this in an RL training pipeline, you then need a supercomputer, and it takes months. So since this wasn't really the goal, we went for a bit of a simpler strategy. What we've done here is we've identified a residual model. So this is the base model. And then we use real-world flight data to identify residual terms that we need to add to these forces and torques that are observed by this first principles model, which is very basic. And we've done so based on physical insights. So you have essentially only the velocity and the motor speed, and then polynomial combinations of these two quantities, which really give you very good modeling ability of the performance of the real vehicle. So if you have that, and you put all of this into your training pipeline, you really think it's accurate, and it should fly quite well. Well, sad truth is, it flies about that well if you deploy it in a vision-based setting. And I do not show you hours of drone crashes, but I could have if I would have included all the ones that are experienced. But, well, you see, drone crashes are not that good for the vehicle, and it terminates the agency of this agent rather quickly. So we need to do something about that. And the interesting thing that we observed is, when we deploy them with onboard vision, we really crash quite often. However, we were able to deploy them in the motion capture system. So what you can see here is now a deployment where we essentially deploy the policy once in simulation, which is the bright curve, and then we deploy it again in the real world using our motion capture system. So even if you have perfect state estimation from a motion capture system that is external to the drone, even then you see a bit of a mismatch here. And if you would deploy this with onboard vision, it only exacerbates the effect. So what we're facing here is what every roboticist has, the sim-to-real gap. Only that ours is actually quite severe and rather damaging to the drone if we try to deploy it. So where does the sim-to-real gap come from? Despite having a pretty good aerodynamic model, we still have unmodeled effects. So for example, turbulence or ground or downwash effects are not really able to be seen by the drone in simulation. Why is that? Because ground effect only happens if you're very close to the ground. You're not always very close to the ground, so simple polynomial models that capture velocity-motor speed relations will never be able to capture this. Then you have things like mechanical effects. You can see over here, the drone, if the camera is mounted to dampers in order to have good IMU signal, not too many vibrations. But that's a huge problem, because thanks to this effect, what you actually observe is that the camera can change its orientation with respect to the main body of the drone. So all these cause problems. And in addition to this, you also have problems from the perception side as well. The illumination can change. We deploy this thing in a hangar, so an airplane hangar. This has windows. It can be daylight, it can be nighttime conditions, etc. The background is different. Sometimes there's more airplanes next to us parked, sometimes less. So there's a lot of change that can happen in the real world. But most of these things are policy specific to one extent or the other. What does it mean? If you have a policy that does a turn in a specific way, this damper effect, this damper elasticity will be reproducible. If you do a fast right turn, you will always have a similar behavior on this one. Similar to aerodynamic effects, the ground effect will be always happening at the same position. A policy that tries to fly a certain trajectory will experience ground effect roughly at the same places. Perception effects, illumination, etc. If you fly within a closed time frame, let's say 1 hour after another, what you will see is the background looks similar, the illumination similar, etc. So all of this led us to the finding that we need policy-specific models. What do I mean by that? We need a policy, we need a model that does capture these effects in an efficient way, but is specific to the policy. So we augmented the training loop a bit by including these residual terms here. So instead of having a simulator that simulates only the physics by the models that I've showed you and then gives a reward, what we actually do is the command or the state that is input into the simulation is augmented with this dynamics residual. What does this residual do? Well, it tries to capture what the policy would usually see at a specific position in the track at a specific point during the race. Similarly, the perception residual will alternate or will disturb the ground truth state here. So with this perturbation that you get, you put the state out here, and then it gets perturbed by the perception residual term before it goes to the policy. So this allows the policy to get used to what it will experience later on in the real world. Now the question is only, how can we get this real world experience into the policy? And here the strategy basically is to first deploy a policy that is trained with nominal simulation. And so when you have trained the policy nominally, you deploy in the motion capture. What do I mean by that? Well, we have this motion capture system around our racetrack, so we can actually deploy the policy that we've just trained in the nominal environment. Then we use a Gaussian process to fit the differences between what the policy sees in the real world versus what it has been trained on. So for example, here you can see a perception residual in the position. This is one of the axes. What you essentially see here is that at certain points in the track, it is always off by a certain amount. So these colored lines represent distinct rollouts of these Gaussian processes, and they kind of fit this mean value. Now, if you deploy or if you train the policy on a state estimate that has been perturbed with this, it looks very much more realistic to what the policy would see when it is deployed in the vision-based scenario. So essentially what you do is you train the policy on the differences between the ground truth state, the Viken-based state, and the perception state that the onboard perception system would deliver to the drone when it flies that policy. And that is a pretty critical aspect here, because this allows us to really get the real-world data into the system. Then you take the same policy. So you basically take the checkpoint that you had, and you go put it back in the simulator, which is now augmented with these two terms, and you fine-tune the policy for a few more epochs. Note, we don't have to train the policy until convergence again, because it has mostly figured out how to race already, and we will only want to tell the policy to become a bit more robust to these real-world effects that this policy will see. Note, we could iterate this process multiple times, because if the change in policy was too big in this fine-tuning step, then of course the residual terms would change as well. However, in practice, it shows that a single iteration of this procedure is actually enough for the cases that we need. And then finally, you can deploy the policy with onboard sensing, because it is now seen the effect that it can be expected to see during the real-world deployment. And if you do this, you can actually win against the world's best pilot. So we invited 3 pilots, just, statistics make it better, so we wanted more pilots than just one. We had Alex Lanover, we had Thomas Pittmader, and Marvin Schepper. This guy's pretty young. When he raced, he was 16, so pretty cool. Especially kids are really fast at these reaction tasks, so actually he was a pretty damn good pilot, especially given that he was 16. And we've raced against all 3 of them. What you can see is, against all of the 3 pilots, we lose a couple races, however, we win most of them. So note, losses are for the pilot. So if this number is high, the AI has won. Down here, the AI is here. So it's Swift, the AI, versus human pilots, and 15 races are won by the AI, 10 are lost. So it's not like we win all of the time. However, I have to say one thing. If we finish the race, we win. 40% of the time, we don't finish the race for various causes. Most common, we crash into something. And this can happen because, for example, human pilots crash into a gate and slightly move the gate, which is a bit of a problem for the state estimation system. Or even worse, they tip the gate over. That is not something that drone policy wants to see. Another reason that you can have is our policy always goes full speed, no matter what. So even if it is ahead miles, or even if the human pilot crashed out, we will still fly full speed, which makes it extremely risky. So the human pilot still has a chance. And lastly, I have to say human pilots are crazy good at flying broken drones. What do I mean by that? Well, a propeller usually has 3 blades for drones. They can even fly if one only has 2 blades. It vibrates like crazy, it makes a horrible noise, but the human pilot still gets the thing into the finish line. So if both drones collide and we kind of cut up drones a bit, the human pilot will be able to fly, whereas the AI does not fly at all if the camera is dangling down or something like this. It's just not possible. So that's kind of where the human really has an advantage here. If we look at it a bit more scientifically in terms of statistics, what you can see here, the AI, as you might expect, is way more consistent. We have a lower median value. At the same time, we also have the lower standard deviation compared to the human pilots. You also see the more senior and the more expert the human pilot becomes, the lower the standard deviation. So Alex Lanover has a remarkably low standard deviation, especially when we compare him to the kid. I mean, the best lap times are very similar, right? But nevertheless, human pilots exhibit a lot more variance. If you've shown 3 laps consistently, that is not a race, but basically race minus the start. So if someone would argue, oh yes, but you only launch faster than the AI, than the humans, then this plot wouldn't be like this, because this shows 3 consistent laps. And also here we are able to maintain a better median, as well as a lower standard deviation than the human pilots. However, you can also see it's not like all laps here are much better than the humans. We're really on par, we're just slightly better. And that is because if you look at the average thrust that human pilots apply, it's about 99%, which means 99% of the track they anyway go full throttle, and you can't go more than that. So we are really on the edge of what the vehicle performance is. And this is why you don't see a drastic change towards the lower limit, because humans are nearly time optimal. If you want to understand why are we then still faster, yes, we're more consistent, but also we have a slightly better lap time. And one of the reasons for that is, for example, that we are able to take turns a bit more efficiently. So blue is Swift, red is the human, and you see the human takes the turn a bit too fast. The human brakes a bit too late and flies a bit too fast to the turn, thus loses time on the way out of the turn. If we then continue to look at, for example, something like the split S, which is this upside down thing where the drones have to go through, here, then you see again, the human approaches it too fast, then overshoots, whereas the AI is able to do a much more round and circular path, which is good for the lap time. If you then continue to look at this and, for example, go the second lap, you see the human again takes a different path here. So there's a lot of variance really in what the human does, whereas the AI takes a very, very similar path all the time. Now you might ask yourself, is it a fair race or not? And this is, I think, a very important question to address here, because if it wouldn't be a fair race, it would be very, very bad for the comparison, also for the scientific value of the work. So I try to argue that this is a fair comparison, despite not having everything identical, and you will see why. The drone itself is both 39 newtons of thrust at the same weight. So we've basically matched both of the drone's weights. The human cameras are a bit more streamlined than the real sensors, which are more like a square brick in front of the camera. So there maybe the human has a slight advantage based on a more streamlined drone. The information that we're able to use is also a bit different. Humans have a 120 Hertz camera, whereas our drone only gets a 30 Hertz images from the real sense, but we also get IMU information. Is that an advantage or not? I don't know. I would argue that having IMU information as a human is essentially useless because you can't parse numbers that quickly. So what would the human do with that? On the other hand, they have a much higher update rate of 120 Hertz, which allows them to kind of probably understand rates, etc., from the feed of images, whereas the drone only at 30 Hertz would struggle a lot more to have a precise body rate estimate or acceleration estimate based on images only. So I think these two are very comparable in terms of input modality. At the start of the race, you've seen initially that the AI drone is much faster at taking off. We have already compensated for the latency of the audio system, so we do not launch the drone when we play the beep on the computer. No, we actually launch the drone when the beep comes out of the speaker, so that it's a bit more fair, because the human could, in theory, if he had instant reaction time, react as quickly. However, even if you take into account a human reaction time of, let's say, 200 milliseconds, which is kind of the expert reaction time that humans have, we still have a win margin of much more than that. We have a win margin of almost half a second against the best pilot, which means even 200 milliseconds more or less do not really change the story here. So I want to highlight that we do not win because of better reaction time, but because of being actually able to race faster, as you had also seen during the plots with the 3-lap races. The biggest downside here for us is really that we are unable to recover after any kind of crashes, whereas humans are remarkably robust. As I said, half-damaged propeller, no problem. Because even more crazy, when the drone flips upside down, humans have like a rescue procedure they can kind of do on the RC that basically gets the drone somehow airborne again, and then they can continue to fly. This is the problem with the rules of drone racing. Because in drone racing, you win. If none of the drones makes it all the laps, the one that makes it further wins. Meaning, if we crash in lap 2.5, and the human pilot takes a minute to recover from being crashed, but then is able to fly however slowly the rest of the race, the human pilot will win the race. So this is something that the AI definitely lacks at the moment. And this especially, goes bad because we can't play safe when we are ahead. So there have been cases where the human pilot was half a lap behind and the AI crashed out in like the last lap or so. And then, the human pilot wins the race despite being slower for 90% of the track. So I think it is a fair race. We raced according to the human rules. I mean, no roboticist would have said after a crash that the race continues, but that's unfortunately the human pilot rules. And we followed these. So I personally think we can call this actually a race as fair as possible for a human against an AI race. And thus it's quite an important step towards really making drones as agile as possible. Where can we go from here? Well, we've seen that this is the first time that a human really is beaten by a robot at their own game. I want to highlight that it's their own game because drone racing wasn't invented by roboticists, but by humans. And there's other things. I mean, yes, a robot or an AI can beat a human on many tasks. Artificial Atari games, chess. All of these are games where you have perfect state information, while you have no uncertainty in a way, because if you look at an Atari game, you have a screen, and the screen has every information. If you film the screen, you have perfect information about the game as good as the human. However, this is a real physical robot, which has a lot of differences. You don't know how the actuators react, dynamics can change, dynamics are hard to model. So this is the first time kind of that a robot managed to beat the humans in such a setting. Crucial for this success was actually the fine-tuning aspect with real-world data. And I believe this is an important thing to note because if you want to do this with other robots, if you want to have other robots beat humans at their own game, I believe that this fine-tuning approach makes them really competitive. It's extremely hard to capture every single bit of information during training and simulation. I would say it's not possible. You can never have a perfect model of the real world in simulation. However, if you can inform your simulation or your policy training with real-world data, may it be by capturing real-world information and then updating the simulator accordingly, or by directly training in the real world when feasible, these things really make the policies competitive. So I think this is kind of to say roboticists need to work on real hardware. It's not enough to demonstrate that your approach is better on Samad Hari benchmark or Mujoko benchmark. You need to show it on the real world robot, because that's where the challenges arise. In simulation, everything is possible. Compared to humans, Swift races more consistently. That's a good argument for actually automating many tasks, right? If the AI is more consistent than a human, then we should have inspection tasks, search and rescue tasks, etc., done by AIs, done by autonomous agents, compared to humans that sometimes make mistakes, especially in scenarios where making a mistake is really badly. However, in order to get there, it's really important to work a bit further on this aspect of robustness and really being able to use the drone still in a scenario where it is half broken, where it has big problems by, the camera is misaligned, it is half fallen off or so. And at the same time, we see that the perception system is very sensitive to environmental changes. I mean by that, for example, the light changes. Sometimes even the temperature can have an effect on how the motors, etc., behave. So all of this is a very important aspect. Similar to human pilots, also we have to train on a specific track. And I believe this is also a very interesting avenue for future work, because what if we could just deploy the drone on any track? Kind of a lifelong learning scenario where you maybe show the drone the track at a slower speed and then try to incrementally update a policy or condition a policy towards flying fast on any track. So there's still potential for this work ahead, but I think that what Swift has shown is we need to work more on real-world robots, and we need to work more on real-world scenarios that are challenging outside of the lab environment. And with that, thank you very much, and I'm very happy to answer your questions.
Okay, so let's start. We have the first question from the audience online. Oli asks, what practically valuable tasks do you think your approach is most applicable to in the immediate future, next year or two?
Yes. So when we talk about practical application of drone racing, what I can see is especially a rescue task, for example. So think of gates as door frames. Somewhat similar, right? Rectangular patterns, relatively easy to recognize as such. And I imagine we would bring this to something that can actually race on multiple tracks by being conditioned in some sense on where it needs to go. For example, you could imagine something that is conditioned on a floor plan of a building. Now, if that building is like, let's say, on fire or something, basically you don't want to go in as a human. I think that having a drone that is able to navigate quickly into it is a very critical aspect here, because this drone might be able to get to a position that has valuable information for example, firefighters to inspect whether a certain structure is still intact in the building. Is it nearly collapsing? Is it not nearly collapsing? That doesn't matter so much to, there's no human inside this scenario, but you really want to get the information fast. So having something that is able to race quickly is super critical when you have no GPS. Another scenario I could think of is an inspection task, for example. The agility that our drone is able to demonstrate means that you can also evade obstacles very quickly. There's a few nice YouTube videos, if you want to look it up, of inspection drones crashing into birds and stuff like this, or other objects that are basically just appearing when they have to do an inspection. And having an algorithm that works on this level of performance and is able to utilize that much of the drone's capabilities makes an evasion of that bird, that other obstacle, whatever, a lot easier than current relatively slow drones, because they have no chance they will just crash into the obstacle. Even if they have recognized it, they are not able to issue commands as agilely as it would be required, despite the hardware already being capable of doing so. So I think these are two kind of separate branches. One is really a direct application of something like a racing scenario, whereas the other one is more take parts of our algorithms, take the insights that maybe neural networks are really good for these because of very fast inference times, compared to optimization-based approaches to do something like emergency avoidance.
Do you think removing the competitive pressure to go really fast and have it be in this race context, do you think removing that pressure would make it more robust to changes of the environment and to a worse condition of the drone?
That's a very good question. So what you're kind of bringing up is the question of how much speed robustness trade-off can you make? And it turns out that if you want to really race, you have to be that fast just because the wind margins are so small. However, what we can see here, I mean, we've experimented a lot with slower policies initially during the development phase of the system. Whenever we have found a new solution to the problems at higher speeds, going to lower speeds would dramatically increase the success rate. So, for example, about half a year after the paper came out, after the paper was submitted, we gave a demonstration in Lausanne, a completely different place. Like we had no Viking system. We were in a completely new arena at like a big robotics event in Switzerland. And for safety reasons, also to like guarantee success in a way, we chose a much slower policy there on a slightly different racetrack, basically an oval racetrack, everything that's space for. But there we were able to just fly, even without the fine-tuning approach completely, at like a speed of about a quarter of what the maximum speed would do. So definitely, if you do not deploy the system at its limit, you're able to really regulate that. Maybe to connect to that, there's a cool idea that we tried subsequently, is also to condition the controls policies kind of on the speed to get exactly that. This is like a first step towards going away where we can say, yes, make the drone race a bit more careful. So it's a single control policy that is now conditioned on how much thrust to weight ratio it is supposed to use. And what you can see here, basically black are the expert policies overfit to one specific thrust to weight ratio. And for example, the blue ones, film C, are one policy that fits all thrust to weight ratios. And this really shows, well, you can train a policy that is able to capture all of these different speeds. And if you deploy one of these policies here at the high thrust to weight ratio and then slow them down to something like here, they become a lot more robust and a lot safer. So this is definitely something that we've tried and had success with. I think, yeah.
Your research was actually cited in an article about different use of drones as less benevolent maybe as a delivery device for something else. You know what I mean? In a less controlled environment. But scaling the limitations, I mean that we are still quite a long way away from putting in an image of where you want the device delivered and then that working with no interference, right?
Yes, so I think what you bring up kind of is, well, how can you misuse this? And I think definitely a lot of people think about the military applications. In my opinion, the military would be rather stupid to use that system as it is at the moment. It does not have a robustness in that sense. It is a really good expert at a single task in a somewhat well-defined lab environment, but especially in scenarios where you're outdoors, where you talk about long-distance drones. I personally think this is useless. And we would not have published the work if you would believe that it is actually usable, if you would really try to use it for such an application like delivering a warhead or so to a target. Because in such a scenario, what you have is you have GPS available, which gives you very good information on where you are. Yes, you can be jammed, but still you can then something like terrain relative navigation. Decades old, like if you go to the B-1B bomber airplane in the US, for example, has a beautiful terrain navigation system that uses like features in the terrain to localize itself. There are systems out there for decades that can deliver these tasks. Transferring these to a drone would be an entirely different task and one I would not work on. But yes, this would be what could be done as opposed to using a purely vision-based system, which is definitely not in its strong point in the open without predetermined features. It's kind of the opposite environment to what we've been racing in.
How good is your drone at overtaking? It looks like you just learned the best kind of path to use the race, but but in reality, when you race, you have other drones which might affect your sports.
It's a very good question, and the answer is we were arrogant enough to say we will always be in front. Our drone has to never overtake. No, bit more serious answer. So if you try to do this as a multi-agent problem, your biggest problem becomes detecting the other agent. If you talk to human drone pilots, they sometimes crash into each other because they're not aware of each other. You have a limited field of view, and especially during maneuvers where you see forward, the other drone can be on top of you, essentially, which is not in the field of view. So in fact, we do not even consider the opponent because it is nearly impossible to detect the opponent robustly enough with the compute capabilities that we are given on board. Nearly all of it is needed for gate detection already. And so we decided to not do it in a multi-agent way. Because having trajectory estimates or something similar for the other agent, while very useful, is extremely hard to get, and also something human drone pilots don't really do. In most cases, what they really do is they just fly blindly, or not really caring too much for each other, and then trying to overtake in a turn where they see the other drone taking the inside line, just hope for the best. So we kind of do a similar strategy, except we never have to overtake. We just hope for the best. There are cases in the split, as in the first lap, since we break earlier where the humans crash into us. Yes, these cases, we just lose the race. We do not have any collision avoidance or any overtaking implemented in the policy. But, also drones are quite small, space is large in 3 dimensions. So we don't crash that often, despite not having actually taken the opponent into account in this work. But it's a very good avenue for future work to do this in a multi-agent reinforcement learning setting and have them like gameplay against each other. Alpha Star, probably from DeepMind, might be one of the references in that domain to check out how to have multiple agents pitted against each other.
First off, thank you so much for the talk. Really cool work. It seems like one of the big advances that got us from sim to real was the introduction of the real world data. Did you guys try doing full offline RL or supervised learning for the policy itself and just remove the simulator entirely?
So the question basically is, can you just collect a bit of real world data and then do offline to learning? So the biggest problem is that a policy that doesn't fly. So a policy that doesn't fly gives you maybe half a second of flight time before the drone hits the wall and you go fix it for about 2 or 3 hours. So you have a very hard time, especially initially, to get the policies to a level where they are actually flyable. Since we then anyway need some kind of simulation training, we've actually not ventured out to then do a half-half training. Also because what you can see typically is that offline RL does not really beat on the PPO algorithm in a simulation if your simulator is good. Like there's very little work that shows that offline performs better. It has more sample efficiency and everything, right? But it usually doesn't achieve a higher peak performance compared to having a very good model available. So assuming we have the perfect model in simulation, doing PPO gives us kind of the optimal reward in the end compared to an offline algorithm. Although that would definitely be something, especially for, let's say, a ground robot, I would definitely try that out. A car that doesn't fall out of the air if you don't give any control inputs is a lot easier to safeguard during the initial learning stages.
Just extension on that, do you think it's possible to, with the introduction of the perception residuals to actually reduce the latency or the fidelity of the simulator so you could have a faster, cheaper simulator by augmenting the real world data?
Yes, so the question here is, can we make the simulator faster by having more real world data instead of having a fancy model? That's kind of the way we went down already. The idea here is if you have the less real world data or less real world residual that you have to put in, it will be more general. The more general it is, the better it is for out of distribution case it hasn't seen during the initial deployment when it sees them during training. So we've experimented a bit with this, going for a very complex simulation, basically using a neural network trained a giant amount of data to then model the entire dynamics. Here we use NeuroVEM, it's the work for this. And it turns out you lose a lot of train time. And this simulator that we then used in the end is as fast as just using basically a single polynomial. Because if you have like AVX2 vectorization and stuff going on in your simulator and everything is beautifully parallelized, we don't actually pay a speed penalty for our residual that we've used inside the simulation. And the main train time then comes from the augmentation. In fact, like querying the Gaussian processes is already the major thing during the fine-tuning step. So having to rely more on the fine-tuning and less on the initial simulation is not something that would actually reduce the train time in this specific case, thanks to highly optimized code.
Thinking about how programs like Stockfish and AlphaGo have impacted chess and Go respectively, how do you think this work is going to affect the racing of human drone races?
That's a very interesting point. If you consider also what the human pilots said, I think what's really cool is the speed matter here, is that he realized that the AI showed something that he's not capable of in terms of perfection. That he even had, he had done some trajectories on other tracks that were done differently by him than the AI chose it. And he was really inspired by this and thought that you could use this as a drone racer to train yourself to kind of look at a reference solution. And I mean, we've talked a lot with these pilots and they were really interested in these aspects of the flying as well. I would still say that for the everyday drone person, I mean, Stockfish nowadays, if you learn chess, you kind of use Stockfish as a guideline, you can evaluate how good he moves, etc. For the everyday drone hobbyist, this is not that much the case. However, I could imagine that at expert level, it will become possible that people use something either like with racing against the AI in a simulation, or even just path planning with optimal paths to optimize their own paths and be able to like fly faster. So I think there's definitely some potential in that. Although given the size or the amount of people that play chess and the amount of people that race drones, I would not expect to found a startup based on, hey, I sell you a good drone racing simulation. That's probably not a business model that would work.
Why do you merge both the planning and the control? Could policy not be created just for the planning unit to keep the modularity advantage? Would you not be able to incorporate the residual information if it was just a policy for the planning unit?
Mm-hmm. So what you're referring to is basically this original slide that I showed where we have a different way that you can basically combine policies, that we use a policy that is learning and control in one aspect, and we just go to the slide, and not that we separate. So basically that we combine the planning and controls part shown here and only use separate localization. What you kind of think of the direction of Raquel Urtasun, autonomous driving, shares a few very famous papers on this, like having 3 different modules. The biggest problem, in my opinion, is here than the controls part. So if you plan a reference that is time optimal meaning it is not possible to fly faster given the actuator constraints. And if you're off a time optimal trajectory by an epsilon, it is by definition not possible to return to your planned trajectory. Why is that? Well, if you have planned exactly at the limits of the system and you're off because of whatever real world effect happens, well, you're already at the limit, so you'll not make it back. This means that you'll be constantly tracking an unfeasible reference. This is something that you should not do as a controls person. It is not a good idea to try to have your controller track something that is, by definition, constantly infeasible, simply because the plan was executed at the limit. And if you then argue, well, then just don't plan at the limits, yeah, but then you're slower than you have to be. So what you really need is something that is able to always fly at the limit and essentially either replan the entire trajectory every time step, or you have to do a merged architecture like we've done. And in fact, my lab has some work on this joint planning and control as an optimization problem. It's called model predictive contouring control, where the idea is that you have an objective that maximizes progress along a predefined path, similar to what the RL has. But then you solve this in a classical optimization fashion by basically formulating the problem cleverly as a sequential quadratic program, SQP. This also gives you very, very good lap times. However, it is much more brittle to having a dynamics that are off initially, especially because with a learned joint controller, what you can really do is you can make use of these residual components, because both modules can learn how the residual or how bad the input from the localization system is. Whereas as you separate these two again, then the planner maybe has access to these perturbed perception states, but the controller then does not really have that because the controller is fed the plan from the planner and has to track it. So this again introduces a level of modularity that costs us a lot of robustness, which is why in the end we actually went for joining these two and only keeping the localization part separate, especially to not have to render images during training.
Yeah. So let's stop here to have the time. Okay. We're gonna have the networking time now, so you can also bring more questions to Leonard. Thank you very much for the talk. Remember, we also have this going on Wednesdays every week now. So the next one is going to be this week. If you want to keep on track with all this side of stuff, please join us. And let's go to something. Thank you very much, Leonard.